So now we're going to go through section 11.5, which is about alternating series. So each convergence test so far has required the terms in our series to be positive. So what about ones that don't have positive terms? So we've had instances where you could have those alternating pieces, one be positive, one be negative. We had sequences like that, so they involved a negative 1 to the n. That's exactly what an alternating series is. So an alternating series is a series whose terms are alternately positive and negative. So pretty much what we have so far in our tool belt is we have the integral test, which when you define the function requires it to be positive. We've got comparison test, both of them require positive terms. But now what about something that has negative terms in it and positive terms? Is this a little bit more lax? Do we have better criteria for divergence? We're going to see different examples of that. So one example you could look at, you've got positive 1/3 minus 2/5 plus 3/7 minus 4/9. So you see it's alternating between positive and negative. The bottom is odd numbers, and then the top is just increasing by 1 each time. So if you were to write this in sigma notation, it would be the sum from n equals 1 to infinity. You've got the alternating start. Because I'm picking it to start at -1, you have to have -1 to the n plus 1. So when you plug in 1, you get a positive term. Now, the numerator is starting at 1 and it just increases. The bottom is an odd number, and one way we can write odds is 2n plus 1, 2n minus 1. In this case, if we plug in n equals 1, the denominator would be 2 plus 1, which is 3. Plug in 2, you get 4 plus 1, it's 5. 3 would be 7, and you get all of the odd numbers. So this is alternating. We could have another example, positive 1/2, negative 1/4, plus positive 1/8, minus 1/16. So if you see the previous terms just getting multiplied by negative 1/2, that's really just a geometric series. So it's initial term, the first one is a, you're multiplying by negative 1/2 each time. So to get from here to here, you multiply by negative 1/2. Same thing from here to here, multiply by negative 1/2, multiply by negative 1/2. So it's a geometric series where you get a, which is 1/2 times r to the n minus 1 since we're starting at 1. And if you want to simplify that and clean it up, you can pull the negative 1 out on its own to see that it's alternating. Then another example we could have is negative 1/5 plus 1/10 minus 1/15. So the bottom is multiples of 5s, and you've got that alternating component. So in the bottom, you could put 5 times n starts at 1, then 2, and 3, and you get all of those multiples of 5, and then it's alternating, so you need that negative 1 to the n. So pretty much you're going to recognize you have an alternating series if it has this negative 1 to the n, negative 1 to the n plus 1, n minus 1, doesn't matter, you have negative 1 to a power times this other piece. That's going to be when you pick off it's an alternating series, and then we're going to probably apply the alternating series test. So the n could go from 1, 2, 3, but what's left over will be some positive number. So you're kind of pulling that negative 1 to the n off to the side, and the term that's left over is important. So we want to figure out, how is this thing going to converge? We can't apply the comparison test, the limit comparison test, or the integral test because they need positive terms, but we have negative ones. So in this case, we've got something called the alternating series test. So you can see all of these tests we've learned tell you exactly what they're going to work for. Comparison test, you make a comparison. The integral test, you take an integral. The alternating series works for alternating series. So I'm going to show you what it says, and then I'm going to explain why that's actually going to be true. So you've got an alternating series which has that -1 to the n somewhere in it. It doesn't necessarily have to be to the n minus 1, but there's -1 to a power. You have two criteria that must be satisfied. The first one tells you that the bn plus 1 term is less than the bnth term. So what this means is those terms better be decreasing. So they're getting smaller and smaller and smaller and smaller. And you want that term to go to 0. So after you ignore the alternating part, what's left over? Do those terms decrease, and does that limit go to 0? If those two things happen, you get that series is going to be convergent. So kind of the intuition of this is if the terms of an alternating series decrease towards 0, then the series is going to be convergent. So we can think of why this actually works graphically, thinking about those partial sums, okay? So we're going to have a number line down at the bottom. Okay. Your term is going to start at 0. And then it's going to keep going. And I'm going to assume that it starts out a positive term and a negative term, but it ultimately doesn't matter. So the first thing is we're going to add the first term. So from this, we're going to add the quantity b1. So you get a positive number. And this gives you that first partial sum. Okay. So here is what S sub 1 is when you add b1. From this, b2 is smaller and it's negative. So starting here, we subtract b2, and it's a little bit smaller than b1. So I'm heading in these directions. So we're subtracting b2. So the second partial sum stops here. This is where S2 would be. So we're alternating back and forth. We had a positive term, we had a negative term. Now I'm going to add b3 to this. But again, it's smaller than b2. So I don't go the full length that b2 was. And this is where our third partial sum would land, S sub 3. Do one more. Now I'm going to subtract b4 because my next one would be negative. And again, doesn't go as far because the terms are decreasing. So you subtract b4. And then from that, you get the fourth partial sum. So you're going to keep doing this process, and the gap between these is going to get smaller and smaller to the point that it's going to kind of oscillate around one specific number. So first we add b1, you add negative b2, but it's smaller, and you repeat this process over and over. So eventually those terms are going to 0. They become so close, you're going to end up around some value in here. S. So basically you're going to go forward some, backward some, and then you're going to keep this process, and eventually you're going to be adding nothing to it, that it'll land to S. Okay? So it ends up somewhere between 0 and b1. So this is a great test, but the thing you have to be careful with is notice that the test only tells you about convergence. So we've had divergence in the other test. This one only tells you convergence. So you cannot say, by the alternating series test, this series is divergent. That's not going to be possible. What we are going to see is if this test does fail, it's probably going to be because that second criteria doesn't happen, so the term doesn't go to 0. In the case it doesn't go to 0, that's exactly the test for divergence. So if you try to use this, it fails, go back and try the test for divergence. So let's try some examples. We're going to determine if the series is convergent or divergent. And we're going to have 1 minus 1/2 plus 1/3 minus 1/4. So you see the denominator is just growing by 1. You can write this as -1 to the n plus 1 over n, and we're summing that up. So this is called the alternating harmonic series because if this wasn't there, it's exactly the harmonic series. So what you want to do is you have to show the terms are decreasing and they tend to 0. You're going to find what you're looking at by ignoring that alternating part. So just take the absolute value. It's going to annihilate the -1 to whatever power you have. This 1 over n is what you want to show is decreasing, and what you want to show goes to 0. So you show the hypotheses on this term. You ignore that alternating part completely. So first thing we have to do, is it decreasing? You could do this one of two ways. You can use an inequality like we've done before. This one's really nice to do the inequality with, so I'm going to show it. Or remember, when you want to see something's decreasing, you take a derivative. So you can define a function, show its derivative is always going to be negative. So let's look at our terms. So Bn is 1 over n, and if you look at the next term, it's 1 over n plus 1. So if you compare the bottoms, n is less than n plus 1. That's true for all values of n. So when you flip them, you get the reverse inequality. 1 over n is exactly Bn. 1 over n plus 1 is exactly the n plus 1 term. So Bn is bigger than Bn plus 1. So yes, this is decreasing. Okay, so the first hypothesis is satisfied. Second hypothesis we need is, does that limit go to 0? And this is really nice and simple. When you take the limit as n goes to infinity of Bn, so the limit as n goes to infinity of 1 over n, that's definitely equal to 0. So we satisfy both hypotheses. So what we can say is, by the alternating series test, the sum from n equals 1 to infinity of -1 to the n plus 1 over n is convergent. So this is very different because the harmonic series is divergent, but as soon as you throw that alternating part in there, it's convergent. Because now you've got these negative terms that are taking away from the sum. So it's decreasing pretty quickly, and it's going to make this sum up to something finite. Okay? So let's do some more examples, but this is all we have to show. We want to test this thing for convergence or divergence, and we've got -1 to the n times e to the -n. So again, first thing you notice is it's got this -1 to the n factor. Take a look and see if you can use test for divergence, but because that -1 is in there, let's go ahead and let's try the alternating series test. So we take the absolute value of this and we want to show what's left over is decreasing and that limit goes to 0. So you ignore the alternating part, you show the hypotheses on e to the -n. Is this decreasing and is this negative? Or does the limit go to 0? So this one's a little bit harder to show in an inequality. So now I'm going to actually go ahead and define that function. So we're going to let f of x equal e to the -x, and we're going to define this for all x greater than or equal to 1. So its derivative, nice quick chain rule, the derivative is -e to the -x. But e to the -x is always greater than 0, so the derivative is always negative. So yes, Bn is decreasing for n greater than or equal to 1. Okay, so you can pick which method you want to do. If it's a simple term that's left over, the inequality is nice. If it's more complicated, probably have to do the derivative. And now we want to see, does that limit go to 0? So if we look at the limit as n goes to infinity of Bn, it's e to the -m. So you want to take the limit as n goes to infinity of 1 over e to the n. The bottom's just getting larger and larger. So yes, this limit goes to 0. So we can say by the alternating series test, this series is convergent. Okay. So nice and straightforward, 2 criteria you have to apply. So let's go ahead and try this one as well. We want to test the series for convergence or divergence. So that alternating part is in there. Gonna be an indication. Let's try the alternating series test. But this is going to be one of those examples where it's going to fail. So this is alternating, but if you make your Bn cosine of pi over n, when you try to take that limit as n goes to infinity, well, even showing this thing's decreasing might be more complicated than you want to go through. So if you take the limit as n goes to infinity of that term Bn, it's the limit as n goes to infinity of cosine of pi divided by n. This is just going to 0. So you get this thing goes to cosine of 0, which is 1. So we don't satisfy part 2 of the alternating series test. So I cannot say here that this is divergent by the alternating series test. This tells me my limit didn't go to 0. Oh, that's exactly what the test for divergence says. So because of this, we use the test for divergence or divergence test. Since the limit of that general term is 1, as soon as you add that alternating part, the limit as n goes to infinity of -1 to the n cosine of pi over n doesn't actually exist because it's alternating back and forth between -1, +1, -1, +1. So by the divergence test, this series is divergent. So you can go ahead and you can try to apply alternating series as soon as you see the -1 to the n. But remember, first thing you should do, test for divergence. And this cosine of pi over n gives us a bit of a problem. Okay? So that's pretty much all there is to this test. It's just showing those 2 criteria. So let's do one more example that is a little more complicated. So we've got -1 to the n times the square root of n plus 1 minus the square root of n. And we're going to sum that from n equals 1 to infinity. So first thing we need to do is we've got this alternating part here. So probably alternating series. So let's go ahead and let's look at what our Bn is that we need to show is decreasing, n goes to 0. So what we do is we take the absolute value to get rid of this alternating part. And now because there is subtraction, I don't necessarily want to get rid of the absolute values right away. What I do need to do, though, is clean this up quite a bit. So I'm going to go ahead, because we've got to show this thing goes to 0 in a limit, I'm going to multiply by the conjugate. Multiply by root n plus 1 plus root n, and then do the same thing in the bottom. Okay. So up top, when you multiply the 2 square roots, those just become n plus 1. The outer and inner are the same thing, but opposite in sign. And then the last term becomes negative root n times root n, so just minus n, over the square root of n plus 1 plus root n. Okay. So our general term without that alternating part is 1 over the square root of n plus 1 plus root n. And now you can kind of see that this term is definitely going to be positive, so we can apply the alternating series test. We want to show this thing is decreasing and that the limit goes to 0. The limit going to 0 is nice and easy. The decreasing part, not so much. So our first hypothesis we have to show is Bn decreasing? Okay. So we're going to define a function, and we want to show that derivative is going to be less than 0. So you could do this for this root function in the fraction for this thing. But I'm going to go ahead and do it for the original one where I didn't multiply by the conjugate, because otherwise I have a lot of like chain rule and quotient rule, and I don't really feel like dealing with all of that. So we're going to let f of x be the square root. Oh, that is not a square root. We'll let it be the square root of x plus 1 minus the square root of x. And we only care about when x is greater than or equal to 1. So we want to take the derivative, and we want this to be decreasing, so we want to see the derivative is going to be negative. So f prime of x, they're both square roots. You get 1 over 2 square root of x plus 1 minus 1 over 2 square root of x when you take that derivative. Now it's going to be best to actually, you could combine this if you want. I think that's going to be the simpler thing to go through. So this is missing a root x. Even better, let's not even do that. Okay. So we need to see, we need to break this into a number line. So we need to make sure we find all the vertical asymptotes, and then we need to find the zeros of this as well. So the vertical asymptotes are going to occur when the square root of x plus 1 equals 0, or the square root of x is 0. So x equals negative 1 is one important point, and x equals 0 is another important point. But honestly, these two don't really matter, because remember, x is greater than or equal to 1. So I don't really care about that happening. Second thing we need to find are the zeros of this. So in that case, 1 over 2 root x plus 1 minus 1 over 2 root x needs to equal 0. So that would just mean 1 over 2 root x plus 1 needs to equal 1 over 2 root x. So we want to solve this equation. We might get some extraneous solutions. That's fine. But we go ahead and cross multiply. The 2's also cancel out. So we get the square root of x plus 1 equals the square root of x. So you square both sides. You get x plus 1 equals x. And you run into a problem, because when you go to subtract x, you get 1 equals 0. So there is no zeros for this function, which is good. So I don't have any important points that this could happen at. So its derivative, f prime of x, doesn't change sign. On this infinite interval 1 to infinity. Okay. So I can pick any number from 1 to infinity that I want. I'm just going to pick 1. So f prime of 1, if we go back up to what f prime is, it's 1 over 2 root 2 minus 1 over root x. So you get 1 over 2 times 1. And if you go ahead and condense this, you're going to see this is definitely less than 0. So 1 over 2 root 2, well, 2 root 2 is like 3 point something, something along those lines. So this is definitely less than 0. So because of that, the derivative doesn't change sign on this interval. F prime of 1 is less than 0. So hence, f prime of x f prime of x is less than 0 for x greater than or equal to 1. So f is decreasing. Okay. And since f is decreasing, Bn is also decreasing. Okay. So our first hypothesis satisfied. We've got one more hypothesis to show, and that one is the nice one. Does the limit as n approaches infinity of Bn equals 0? Okay. So we have the limit as n approaches infinity of Bn is the limit as n approaches infinity. We can use our nice simplified expression. 1 over the square root of n plus 1 plus root n. Both those radicals are getting larger and larger and larger. This definitely equals 0. So Bn is decreasing, the limit equals 0. So we can say by the alternating series test, the sum from n equals 1 to infinity of negative 1 to the n times the square root of n plus 1 minus the square root of n converges. Okay. So this is our first tool we really have for negative terms in our series. We're going to learn 2 more tests in the next section, which are the ratio and root test. And those will give us even stronger criteria, and we'll learn about something called absolute convergence.